Great. Okay, welcome everybody. Thank you for being here. And super excited to have here John Richards from the University of Nottingham and Agnes Cameron from the Creative Computing Institute at UAL. And this is a really exciting and fascinating talk and presentation we're about to have here. The title of Critical Sound Synthesis. And I feel like this combines sort of several of my favorite things. We have sort of on the humanities side, a kind of maybe a critical and speculative practice of some sort. We've got doing amazing things with tiny microcontrollers, so there's no small bit of engineering here. And then also an experimental arts practice of making amazing and wonderful sounds. So I will hand it over to John and Agnes from here.
Thanks for having us, guys. It's really nice to be here.
So I should start. This is Agnes. I'm John. We go back 10 years, possibly, and we have a connection in Leicester, which is in the middle of England. I actually met Agnes in Birmingham. We did a workshop there, and you were, at that stage, doing an engineering.
Yeah, I was an undergraduate engineering student.
Yeah, and Agnes thought Leicester was a very boring place, but then realised there were some things going on. And we had a favourite pub in Leicester called the Swan and Rushes, where we would go and talk about things. And we did concerts. And then Agnes went to America.
Yeah, spent 2 years at MIT. I actually did things that my undergrad was in electronic engineering, but then I went there and I abandoned the electronics for a while. I got really into the decentralized web. I did some open data work. I moved to New York for a bit. I came back. And then since then, I've been working in UAL. I work as a technician there. And a year and a bit ago, invited John to come and give a workshop with our students, which is the birth of this creature that we've brought with us today.
Yeah, that was about 2 years ago. So it's taken us 2 years to get to this point. Probably not due to the complexity of it necessarily, but other things in life got in the way a bit. And coding, of course, you know, there's always something. And I took it upon myself, like I do with quite a lot of the tech I work with, to explore something new. So I've done projects with other microcontrollers before. I like the simplicity, well, I say simplicity in terms of design. You've just got one small microprocessor to work with, working with limitations. So in my world of making sound, I would often pick a chip or a particular set of components and treat that as a kind of limitation in terms of creating sound, in terms of composing. It borrows a little bit from this idea of composing inside electronics or kind of creating music using coding techniques. But the limitations are quite crucial in many ways. And also that you could almost think of it as a sort of material limitation as well, in terms of the particular chip, the way of working with the chip, and then the resulting sounds that you get. So we took it upon ourselves to work with a STM32 microprocessor. This is something I hadn't worked with before. You might not be familiar with that. But one of the reasons was that it came actually in a really small package, an 8-pin package. Also this idea of economy. Yeah, you don't want to be working necessarily with a microprocessor that has excess peripherals. You know, we live in an age where you buy one and you get like 10 free. I mean, I don't want all of the ins and outs, extra timers. You know, so many possibilities. The complexity makes decision-making very difficult. So trying to find something, a kind of small package that would do the job for me. And of course, if you've worked in synthesis, speed is everything, time, something with a really fast internal clock. Anyway, so the journey started thinking about what can we work with. And we came up with this small microprocessor. It's the STM32. I think it's got a 64 megahertz clock speed, memory.
32 kilobytes of flash, 8 kilobytes of RAM, more than that, more RAM than that.
Yeah.
Yeah, we've got a tube of them here, if anyone's interested. Maybe we can pass the tube around. Here you go. Makes a good sound in and of itself.
So that's it. So designing a workshop I quite like the idea, we'll get onto this topic of collaborative making as well. So it's not really product design. I must admit I'm probably a frustrated designer because I like designing things. But we were thinking of creating a kind of way of building something that's very quick, something you can construct in a couple of hours with very limited knowledge of electronics. And this sort of topology or design methodology is something that I use quite a lot for different circuits. It borrows on the traditional breadboard concepts. I think electronic engineers would bang nails into literally breadboards and wrap bits of wire around the nails and create prototypes like this. And of course, we have the contemporary breadboard that people use today. But also, this is great because you can touch it. You can use crocodile clips to reconfigure things. Yeah, the crocodile clip is one of my favorite connectors. It's non-gendered for a start, so that's a good thing. And you don't need a silly adapter. You know, you can just connect it on. It's the answer to possibly all of these annoying adapters that we have to live with. So the idea was to work with something that we could, that was kind of accessible, but that we could also work with in a kind of broader community in terms of working with this technology. So other people getting an opportunity to make things. So this was the kind of starting point. Maybe you can carry on the story.
Yeah, so John came to CCI to do a workshop. John does a lot of these workshops, and I had in fact gone to one when I was 19, and that had, I guess, been a big influence, I think, on me. And it was great to have him in the department. A lot of the work that I do as a technician is trying to make these really complex and, you know, very, in some ways, like intimidating pieces of technology, things that our students feel like they can have agency over and use and kind of have a material practice within. And of course, maybe the crocodile clip is a great example. That's something where you are very close to the materiality of the thing that you're using and working with. And I think the thing that maybe has been the kind of meta project in the workshops that we've been doing with these chips is to bring the materiality of what is in some ways a very abstract object and actually make that material for the students. And I think that happens in a number of ways. I think having to work physically with soldering is always a great way to make students feel like they can interface with and interact with this chip. But another one is, I think, actually kind of addressing the code directly, talking about what's going on inside of this thing. And I guess when we worked on the chip, so John did the initial version of this, which had one potentiometer input. It's now got two, and some code that was kind of just switching between a few modes and a single control. But after the workshop, John was like, we should work on this together. And so we decided, we took it upon ourselves to seek out frequency modulation synthesis. And that's normally where we stop, but we thought for this crowd we would explain that we in fact faked frequency modulation synthesis because we couldn't figure out how to get one of the other timers to work. And so we instead have something that just skips every few ticks and then merges, changes the phase of one of the waves. But you get the same kind of effect. You get some really funky harmonics and some really beautiful sounds. And there's something that was I think for me, as someone who studied electronic engineering, but in a very theoretical context and really never got to actually do a lot of this, the learning curve of actually having to sit down and talk to registers and really get into the weeds of this chip. And we've used all of the flash on the chip. The final version of our code is, I think, 31.5 kilobytes of flash. We really, really went to the limit, and that itself makes it feel super material. You're suddenly you can feel out the space of this 8,000 registers that you're flipping bits in, and that feels very different to talking to a computer where the sense of storage is so much further removed. Maybe John, you have this fascinating brown diagram in your slides, but yes. Maybe do you want to talk about what that is?
So, a bit more background. We will talk a bit more about how how it works and some of the idiosyncrasies of this particular platform and chip. The idiosyncrasies, I mean, I've been teaching straight music composition this term at the University of Nottingham, and idiomatic composition or writing for a particular instrumentation is something that I thought, hold on a minute, that's what I'm doing with a microprocessor. It's totally idiomatic, creating sound purely for one type of device and getting into that. So I could talk a lot about the idiosyncrasies of this particular chip, but we'll come to that. But I want to talk a little bit about some more background stuff, really. I'm mainly known for my work as dirty electronics. Now, John is a very common name. Well, it used to be a common name. So people easily forget that. And in many ways, this term I've used for this talk, or we've used, critical sound synthesis. I mean, dirty electronics is, in many ways, a type of critical sound making. I've been involved in this sort of practice for 20 plus years. Initially, I was studying at the University of York, a music degree, locked away in a computer room, which was great fun at that particular time. It would take a long time to process the sound, and working on the command line with a silicon graphics machine, I think. I found that very exciting, just the hard work and the labor of doing kind of computer music. But it became a little bit isolating, and I very much missed the kind of social fabric of music making, and also doing stuff with my hand, the whole kind of tactile thing. There's a great book by David Sudnow called Ways of the Hands. Fantastic book about how we talk and learn through tactile interactions. And I was thinking, yeah, a lot of my music making is involved in that, playing the guitar, playing the piano. It's all shapes and patterns and thinking about my hands. And also the social aspect. You know, this is a really important thing of music making. And the more I think about it, I could talk about Christopher Small and musicking, and it's all about doing things, making. It's not just the sound itself. So I, in a kind of critical way, said to my supervisor then, oh, sod it, I'm not doing any more stuff on the command line. I want to just work with some analog electronics. And then one thing led to another. Some people could say that was part of the zeitgeist, sort of post-digital movement that came about at the turn of the millennium. And I suppose I was part of that kind of movement, I could call it, in 2000, around about that point. And noise, of course. I was hanging out with a lot of noisy musicians. Some people called it noise, some people called it noise music, some people called it sound art. I was in the world of sound and noise and music, and all those things kind of overlapped. And the word dirty electronics seemed to be a nice kind of term to talk about, you know, to combine these things. And then somehow there's lots of, kind of overlaps, which I think about when trying to explain this, and how perhaps one gets to this stage. Is it physical computing? I could have included that in there as well. Kind of speculative design. This idea of reductionism. I'm not sure it's low-tech, possibly. There's a bit of kind of lo-fi aspects of it. Is this lo-fi? But actually, in the middle, it's got a supercomputer. This was a discussion we were having on the tube. It appears low-tech, but there's technology. At every stage, there's questions being asked about the technology. So yeah, here's my onion, and a few things that maybe tie some of my approach together. Okay. So yeah, here's maybe some of you might consider yourself in these areas. And I was speaking to Andrew over coffee this morning. Yeah, I'm in a music department, but I do have a lot of interest in technology and computing and electronics. And I've always had that interest in terms of trying to get out of the discipline that I've ended up studying. That always exists. I mean, it's true also with Agnes, who last night played the oboe with the synthesizer, which was interesting as well. I've written a few 9 papers. I know that Andrew's written quite a lot of... one more bit of background before we move on to how it... and this is with... actually, Amit Patel is also here. co-author on this paper, the one knob to rule them all. This was with John Bowers, who you might be familiar with. I called this a bit of guerrilla research. John and I decided that he would come and sleep on my floor and bring some students, and I would go and sleep on his floor and bring some students. Fueled mainly on beer and funded by our own pocket money. But it was a great project between De Montfort University, where I was at the time, and the University of Newcastle. And we thought we'd try and break the system by having as many authors as possible in the author title. 12 people in total, I think, roughly took part in this project. Also, we worked with somebody in Shanghai too. But this idea, one knob, trying this reductionist approach to design, working with limitations. So part of my journey, I suppose, has been getting less and less rather than more and more. A little bit like my hairline, as Lorenzo pointed out earlier. So the reductionism is kind of happening, which will interestingly lead us to this idea of entropy in a minute that we're going to get onto. But so there's a couple of kind of background texts here you might want to look at. This did win Best Paper at 9, incidentally. So there you go. A bit of guerrilla research can sometimes lead to some positive results. But it's full of ideas. We're just like outpouring of ideas. And we try to cram it all into the limitations of the word count with the conference. And it's another paper where this actual little synth, I'm going to call it a synthesizer, or is it a generative artwork? Discuss, but More Raw gets its title from this, another project with John and University of Newcastle and Tama Art University in Tokyo. So I've been lucky to work frequently with Tama Art University in Japan. They've got a really interesting kind of approach to design and sound. And so this, we thought we'd try and do the same. We often start off with a provocative brief, something just to laugh at or get us excited. So this title this time was Raw Data Rough Mix. That was the idea. Themes, again, that overlapped with a lot of our interests. And there's a funny line. This line here, you can see it, which I got to admit, John Bowers, this bit, down the bottom. My Canadian friend said, no, I don't pronounce raw like raw, but so I had to change it to some English dialects, pronounce raw like raw. So hence this little synthesizer is called More Raw, which is a pun on raw and raw, but it takes its energy, if you like, from this idea that we were discussing. Last week I found out, this is rather careless, that Robert Plant also has written a track called More Raw. So that's really bad. But Agnes thinks it will be great if we get sued.
It would be excellent if we get sued. Robert, if you're listening, come at us. Maybe what we could do is maybe play the synth a bit and then talk more about how it works and what's going on in it. John, do you want to maybe fire it up and then we can
So yeah, as you can see, I could talk quite a lot about the background and a history, the journey. My journey is quite long in some ways, but there's a few bits from papers there. You can find out about all the stuff I've written and also what Agnes is doing on some of the links. But we're going to talk now about the thing itself and some design ideas and play it a little bit. And then maybe we've got some questions we can answer. Here it is. I'll switch it on. Now, what happens when you switch it on, Ag?
Well, let's play it first, and then we'll talk about it.
All right, okay. Okay. Doesn't sound very interesting. So you're here, it got a bit noisier. the more I was playing with it. And we like this idea of something that's, like I said, more entropic. So it's got these entropies. And the more you play it, the more entropic it becomes.
Before we go into this, do people know what we mean when we talk about the FM synthesis algorithm? Is that something that anyone would like us to explain? Cool. So
are you going to talk about FM first?
Good, and then we can talk about the wavetables. Right?
Yeah. Okay.
Yeah.
What is it? Let's go back. It's direct digital synthesis, which looks a bit like this. Because you don't need many components, right? It's PWM.
So the way the frequency modulation synthesis algorithm works is we've got very few inputs, as has been observed, right? We've got 2 knobs and a button. And to produce a complexity of sound, we decided that we would use a form of modulation that's quite complexifying. So frequency modulation is where you take the frequency of one wave and you modulate it with the frequency of another. The algorithm looks like the modulated frequency equals some constant plus the sine of the carrier frequency times the time. And what this ends up with is one wave shaped by the frequency of another wave. And one of the reasons the synth sounds like it does, there's lots of other things going on, but the frequency modulation part, the Yamaha DX7 is a very famous example of an FM synth. But the reason that the synth sounds at some points a bit like a woodwind instrument, and in part the reason that one of the things that we've done, and I've done, has been to experiment by combining the synth with woodwind instruments, is that that's very similar to what happens inside the tube of a flute or an oboe. These waves layer on top of each other. And it's very interesting because even with pure waves, with very simple waves, you have an incredibly complex sound that can be complexified with very little influence. Just turning the dials produces a lot of richness. And it's really from that point that we were able to then write a bunch of modulations that work in very, very similar ways and do very similar things, but actually do something that's quite complicated.
Yeah, I suppose one thing it's using FM, it's more for less, isn't it? You know, you've got such a set of limitations, this type of synthesis, by just combining 2 waveforms, you can get complex results. So again, the idea of using simple methods to create complex sounds is one of the rationales for using that particular technique.
Where are we going on these?
So, yeah, in terms of, I don't know if anybody's ever tried to make any synthesis with this sort of stuff, but inside, it's a wavetable synthesizer, and you can have fun creating lots of interesting wavetables. This is my fractal waveform, which is quite fun. It just sounds like a cheap organ, actually. But it looks amazing. This is the Weierstrass cosine function. So I would muck about in MATLAB and produce some fancy waveforms, and you can create lots of different sounds from that. It's got it's a 8-bit, only 8-bit, for reasons in terms of resolution and the overall quality of the sound. So it's got a tiny little wavetable that's in 256, 8-bit, and it uses PWM, direct digital synthesis, to generate a pulse, which you saw in the previous slide, this one here. And then it's got a DIY DAC, the digital to analog converter. It's just made with an RC filter on the output. So the whole thing is made from scratch, essentially, those bits that can be made. Yeah. So the DAC is quite significant as well in terms of the quality of the sound, where you get the cutoff point, the spectrum in terms of what bandwidth the instrument has. All these things are interrelated. They're not really something in isolation. If you get it wrong, I've got there's no such thing as wrong, possibly, but things like this where you get ripple, particularly at higher frequencies with a waveform that's got harmonic content. You could think of these as part of the idiosyncrasy, possibly, of the sound, rather than poor synthesis. So those sorts of things come to the fore when you're working with limitations, or the aliasing, or the bad sampling, which comes into play. Those sorts of artifacts, from a creative point of view, can also be thought of as something you can work with musically. So a lot of the early sort of work was just trying to hit the sawtooth, trying to represent the waveforms and exploring with the analog electronics as well. Really simple stuff on one hand, but then I quite enjoyable. A lot of it is down to the listening, ultimately, at the end of the day. So we were talking about the kind of method. As well as seeing it on an oscilloscope, so a lot of time listening to, can I hear that harmonic? Oh, that's got a bit of distortion in it. Yeah. Ultimately, at the end of the day, it ends with our ears. We are analog. There's no such thing as digital sound. There you go. It all ends with our ears. And my studio involves just one small speaker and a breadboard and flashing the code, listening back, flashing the code, listening back, just endlessly doing that. So that was the starting point.
Should we talk about the entropies?
Yeah, entropies. So, yeah, there's a load of synthesizers, right? I mean, not another one, as Brenda would say. Not another one. And actually, after the pandemic, I mean, I've been involved in designing lots of things. Like I said, I'm a little bit of a frustrated designer. These kind of almost like coffee table synthesizers, as I call them. And I've done some for different festivals and record companies. But after the pandemic, back to this idea of critical synthesis. Do we need all this stuff? How many oscillators does an electronic musician need to make sound? You keep buying, your modular gets bigger and bigger. I mean, you only need a couple of oscillators, right? So it comes a point where it's just consumerism gone mad. And I'm just as guilty as well. Look how many bloody synthesizers I've made. They're kind of designer things like this. It sits on somebody's coffee table and they've got their Fact magazine or something, I don't know, a Vogue or whatever, and they're sat down with their headphones. And it's a great thing to play, and I'm maybe guilty in that sense of adding to consumer culture, but we can get on to that in a minute. But entropies. So we decided.
After we made it good, we wanted to make it bad.
Yeah, well, it's all relative, right? Yeah. No, that one. Okay, you talk about entropies.
Yeah, so that wavetable, the way that direct digital synthesis works, right, is we've got this wavetable that we're reading from to do this FM synthesis, right? This sine function and then the sine of this whole thing. This is all read into a single, reading from a single waveform that's defined at the start of our code. And I can't remember how we exactly started talking about it, but we were both getting very into this idea that the waves should somehow rot, and we got really interested in the idea of making a synth that, like, the more you play it, the less, like, usable it becomes. And the way we've kind of done it now, when you wake this synthesizer up, so it's got these two dials on it, and when you wake it up, depending on the initial positions of the dials, one of them determines the way that the waveform rots. We came up with loads of these. Some of them are well known. Some of them were kind of invented. They work differently, but all of them in some way lose the original information in the sine wave that makes up the core of the carrier wave. In addition to these entropy functions, we've also got different modulations. So these are ways in which the waves are combined and which noise is added. But the core thing that you hear every time this mode switch button is pressed, what you hear is the wave becoming in some way more noisy and more entropic. And the only way you can now, we actually, as a mercy to our buyers, we've made it so you can hold the button to reset when the wave just destroys itself. Initially, you had to turn it off and on again in order to get a wave back, but that was deemed too mean. Yeah, it was, I think, like, in a way, actually artificially studying the ways in which these noise forms and entropy forms get introduced into waves was a really interesting kind of study in itself, and it felt like a really fun limitation for us to work with, to just kind of have a sound which mostly transformed itself through losing information over time.
Yeah. I mean, ultimately, I was agonizing over, I mean, it'll just go to silence, like DC offset, you know, eventually the waveform just hits DC. And are people going to get annoyed about that? But so, conceptually, as an artwork, I had to stick to our convictions. You know, that's good. You've just got silence. You've just got DC. But ultimately, you want it to be also flexible. So I kind of agonized over the kind of more conceptual side of it, and the usable sorts of sounds that, you know, people might want to use. And that was a lot of fun exploring that, and we've only really scratched the surface with this. Yeah, again, I was stealing some ideas from my first year composition students, like we were doing a bit of Hockett, and I'll take that into the synthesis. Yeah, that's where you clap a pattern and you clap in the gaps, and there's all sorts of processes, not only in computing, but in the natural world and in music, that you can borrow from in terms of thinking about entropy, as well as some more standard things here, like waveform resolution, like bit crush or something like that, or DC offset or bitwise operators. All of them lead to different sounds. Shall I play a bit of the video?
Yeah, let's definitely do that.
I tried to isolate the entropies without any of the modulation. So this is, let's plug it in. Very dusty oscilloscope, apologies for that. Oh, we're in. But you do get some interesting.
This is the top to bottom entropy, which swaps the top of the wave with the bottom of the wave every time you interact with the mode changer.
I think that's bitwise.
Oh, sorry.
Yeah. So as you could see, with some of the there's different functions. I think this one is a bitwise operation, and wonderful patterns and shapes, and all these slightly different harmonics with these types of entropies. Basic shuffle. This is your triangle smash. Triangle smash.
Put one triangle wave into another triangle wave in different chunks.
Yeah, and yeah, and so you get stuff like that. So yeah, a mixture of listening, concepts, and combining them.
Oh, this is the bit crush one. Should we play that?
Yeah. Oh, it comes back.
Some of them come back, yeah.
So you can see, again, from a very one wavetable, it's just endless possibilities. This thing, even though you're working initially with something that seemed very limited, like one 8-bit wavetable. I mean, we haven't even talked about, then we can modulate these things. It becomes complex quite quickly, even though you're working with something essentially very, very simple. The whole thing here cost about 50 pence. You know, it's an extremely economical way of exploring sound. And actually the synthesis, the reproduction, if you like, of the waveforms is excellent as well. It's very high resolution, partly due to the internal clock speed of this little chip. So you can do very interesting things with synthesis. It's mono, of course, ultimately, but nevertheless, from a creative point of view, there's lots of opportunities you can explore. Maybe we should just go to some questions. What do you think?
Yeah.
Let's have a quick look. Maybe I've missed a few things. Well, yeah, maybe the idea of critical sound synthesis. Well, I've kind of stolen this a little bit from, well, it's critical design, right? From Anthony Dunn, Garnet Hertz, critical making as well. The series, Canadian set of publications. I mean, it's all critical, right? But there's a school of thought, right? Critical thinking, critical design. Critical sound synthesis suggests that it's maybe not just the sound per se, but through synthesis we can also question or interrogate other things in our everyday lives. Perhaps consumerism, perhaps other political things. So this idea of an activism through sound.
One of the things we were talking about on the train this morning and kind of thinking about these synths and what they do is also thinking about how whenever you work with low-level electronics, you get very much exposed to the military infrastructure that allows these, and financial infrastructure that allows these chips to exist in the way that they do. I had a student come to me on Wednesday. Obviously, we've had like an incredibly busy week, but there's a kind of classic thing that I was describing to John. I don't know if anyone's familiar with the term nerd snipe, where you come and you ask the right kind of question. It's just, you know, she was like, well, tell me about how this chip works. And of course, that was like, well, I've got to spend an hour like talking to you about this now. And we had this really interesting conversation, but it ended with that tube of chips that's being passed around. We were sitting with it. And, you know, I was talking to her about registers, and we'd like found, you know, we'd done some maths. There's 8,000 of these, you know, 32-bit rows on this chip. And she's like, how does it fit in there? It's so small. And I think it's really worth thinking about that. Like, how has that been fit onto that chip? The infrastructure that exists to make these things happen, that hasn't happened by accident. That has been the focus of many states and international supply chains to make something that small. And actually, in lots of ways, these chips represent an extraordinary amount of ecological and social violence in their creation. And what's been really interesting, actually, in doing this project, we've actually come across ST microelectronics workers in Grenoble have been striking recently over the company's lack of transparency with work with the Israeli military. And in general, with any microcontroller, with any chip, you're working with technology that is always also being used in weapons. And I think, like, it feels very important to talk and think about that, and think about the way the world's been organized around the production of weaponry, of communication systems, all of the infrastructure that's in place to protect the supply chains that allows these chips with 8,000 registers to cost 80p, 50p. That's mental. That's like obscene. And it's really like, as people that work with these materials, I think it's really important to think about the materiality of that thing, what it's taken to kind of get it onto a board.
So ultimately, this idea of questioning the means of production, I certainly wouldn't in any way profess to taking a moral high ground here, or this being ethical in any way, because it isn't. You know, actually, this board is made in China. The chips probably, well, it's the French, Italian, American multinational. They're all connected to the S&P 500. You know, the stock market. I mean, your head starts spinning, but just through kind of breaking things down into these small components, you start thinking about these things, right? It's made me think more about it. So that's part of this idea of critical sound synthesis. It's made me think more deeply about my relationship with the technology that I'm using and working with.
Computers allow you to be really comfortable. And that
Yes.
comfort is something that masks a lot of the things which go into the things inside computers. And I think that idea of encountering things in a more material way, you start to really worry about them, I think.
So from the raw materials themselves, from the mining through to its distribution, it's just mind-boggling. The carbon footprint of that tiny chip is just incredible. And in terms of how it shaped history as well, I mean. But you can't make one yourself.
Yeah.
I don't think, no, I can't, no, it's the no.
I think you can't. I think you really can't make one of these yourself.
No. And we also had a rude awakening during the pandemic where chip production halted and you suddenly realize that everything's got a microchip in it. Yeah. Is it Eduardo Cat, a microchip in my body? It's like seminal artwork where he sort of implants a chip there. It's coming soon. We're more or less there already, right, with the phone and always at hand, close to us. So, yes, a kind of sonic activism, if you like. Okay, and where we can conclude. Yeah, a couple of books here. Inside the Black Box, Technology and Economics. That's a book I've been reading recently, quite interesting. Again, not part of my main research, but these are sort of books that sit around at home in my house, and I'm kind of drawn to it, and I feel I should be a little bit more rigorous with it. It's fascinating. I'm being drawn more and more to that. Finally, I think we mentioned briefly this idea of like the workshop, but collaborative making is also fantastic for design. So this has taken 2 years, and maybe we've done together 2 or 3 workshops, and I might have done 5 workshops. So if I worked for Google or something, they would call this kind of like they give it a trendy word for kind of hot housing ideas or rapid prototyping. Maybe there's a word for it. But ultimately, in my case, you get a lot of people, you come around, you start making things. But that also informs the design. One way you could say, well, I'm giving to the community in the sense that they're learning something or having recreation through making these sound objects. But also I'm learning from them, what sounds they like, how they make things, how they interact with things, a conversation, a bigger conversation. And before you know it, we've actually workshopped this with hundreds of people already before we've got to this point. And this is journeys. These are different journeys. Stripboard, this version, that version. It's classic design. You go through iterations, but it's using public engagement as well to advance your design at the same time. So it's got a kind of there's an ulterior motive sometimes of doing these workshops in that you can learn from the people and listen to the sounds and how they engage with different practice. And some of the design ideas have been fantastic. So last night we finally, I don't know what a release in this world is. Is it a synthesizer? Is it an artwork in its own right where it's degenerative? We also like the idea on the chip you can store other stuff. So there's mine and Agnes's up-and-coming publication is, in fact, just a text file on the chip itself. So there's I'm not sure how the ref would judge that, but in terms of publication, it's data. I can store data on this thing, not just a wavetable. I can disseminate other ideas in text or something else. So when you download the code, which is on GitHub, you can also read some ideas in one of the include files in the code itself. The code per se doesn't do anything, but it needs our conversation to compile. So this idea of what is it? It's a different way. What's a release? So last night we had a launch party, and I've got a bit of a hangover, and lots of people made some wonderful music with it. So this idea that we can talk technology, but you can also encourage this sort of community of like-minded thinkers, a community of practice, where sound and music also derive from it. By itself, it's kind of generated sound, music, interest, and activity. So the workshop and doing that kind of development has been really, really useful.
Yeah. Yeah, and just we just emailed everyone that had made one of these synthesizers. And at that point, I think we've probably got like 150, 200 people in the world that have a version of this synthesizer. Some people have old versions as well. We gave a bunch of these out with old versions of the code on it. They're all, different kind of eras of it in the world. But we invited loads of people to come and play them last night. And what was really cool, we were talking about this, was that I had really been like, everyone is going to be fed up of hearing blip, blip, blip by like 9 p.m. But everyone actually had done such different and lovely and strange and interesting things with the synths that were not things that we expected. Or some of them we expected, but some of them we really didn't. And it was great to hear it live.
I have a playlist, but you can find it on the website, and so lots of interesting music.
Do we take some questions now?
Yeah.
Yeah.
All right.
Wonderful talk, thank you. I have a bunch of questions, but maybe I'll just start with one. Around the idiom of the microcontroller and kind of, what is that idiom? And then also, like, how much is it intrinsic to that device itself versus the things that you build on top of it? And I was thinking about, like, okay, so, idiomatic patterns of instruments, ways of the hand, this kind of thing. What is the idiom of a piano? What's the idiom of a violin? Sure, I mean, that suggests certain things, but then Bauer's infraviolin, what's the idiom of that? I mean, ultimately, is the idiom just of the piece of wood, or is it of the thing that you've built on top of the piece of wood? So I guess maybe the question that I have for you is, to what extent is the idiom kind of intrinsic to the thing that ST Micro is supplying you versus, layers upon layers of things that you're building on top of it?
A couple of thoughts. So when you get, ultimately, I should have learned assembly language, trying to get as low as possible, right, into the code. But it's hard to do that these days, and it's a massive investment. So it's all written in C, but it has these higher order abstraction layers. It's called HAL libraries. So each microprocessor, I suppose it's a way of creating objects or efficiency within the code that you kind of try to avoid. You try to work directly with the registers, but it's got this particular chip has its own, it's called libraries. Maybe you want to say something about that.
Yeah, the programming, I would say, I think there's two things that feel idiomatic about working with a chip like this. One of them is just the limitations of the libraries, which in a sense are also, and maybe this is also true of physical instruments, that, if you think about extended technique, a lot of that is kind of getting a fuller range of sounds by extending the kind of physical limits of the instrument. And I think extended technique for us would probably just be getting better at writing code for the HAL library, or indeed ditching it altogether. I guess there's also this kind of informational aspect, which is funny because in some ways there's a version of this code which will run the same way on any chip, right? That you can theoretically get to the same point and you can get to the same place. But I do think that there's something in the process that you have to go through to get a sound out of this chip. A lot of people that we've given this to feel like they're playing something that's been composed rather than playing an instrument of itself necessarily. And I think that kind of composition process, the building up of the modulations and things like that, that feels really linked to the information structures that we've been dealing with, and kind of the things that this material thing prioritizes as ways of use. And I think, in a sense, you can get any sound out of a violin, really, if you try hard enough. And I think maybe that's kind of the similar idea here. It's
Well, also it's about speed at the end of the day. Everything is time. And slightly slowing it down into one line of code, and you're going to get a slightly different aliasing or harmonic that might occur in the resulting sound. It's all about speed, and it's not just about optimizing speed, but the impact of that on the sound itself, and that in combination with the DAC, the digital to analog converter, the filter. So these are highly idiomatic in terms of how the sound results and the harmonic content at that point. So this actually has a second order filter in terms of filtering out some of the high PWM signals. So it does have a slightly, well, I don't say sophisticated, but it's a second order filter. Those sorts of things, ultimately, it is in the code, but it's also how it materializes the sound, how it combines with the digital to analog converter. I mean, this idea of the digital analog converter as an instrument is something I'm interested in, because many of us, perhaps in this room, have ignored the importance of that. You take it for granted that that is just something that reproduces the sound. But no, it can change the sound. You can add here, instead of really small capacitors, if I add a larger capacitor, it's quite a slow filter then, and you get a weird sort of glissandi coming into some of the behaviors of the sound. It changes the quality of the sound itself in the DAC, in the filtering itself. So you start again thinking about what capacitor, what size of capacitor. Yeah, what first order, second order. I'm building a DAC as well to go with the synthesis. They're not things in isolation. So I'm thinking more holistically about these things, where it's not always easy to do that when the sound's coming out of my computer here. I can't get into that point somehow in the sound I'm generating on my computer at that sort of lower level. So you find that it does have some idiomatic quality about it. Because I've done similar projects using different microprocessors, PIC chips, for example. You can do this with any microprocessor. And the resulting sounds are different in terms of the quality of the sound, the harmonic content, also the way in which you interact with it. So we can talk about the sound itself, but it's how you engage also with the device, which becomes part of its idiom. So we see an example here, this design versus this design, quite a different way in which you might approach this object versus how you might approach this object. In terms of the, well, we could call it interface, but that point of engagement, if you like, how you engage with the technology is also idiomatic in many ways, and does, the gesture, if you like, does impact the making of sound. I don't know whether I've answered your question, but a few points.
Thank you so much for a wonderful talk. I think I'm curious. It could be like obviously a very short answer. Just sort of, when you say, you're relying on listening to sort of guide some of these processes, is there anything in particular that, stands out? It could be like, I like the sound. I really think this, drives my aesthetic and drives what I'm doing, drives my practice. Or anything like, it's working, it's doing the thing that I thought it would do, it's not doing the thing I thought it would do, and that works, etc. If there's any sort of like, or this is interesting, I find this interesting, but I don't know why yet, this kind of thing. Yeah,
so, I mean, the worst thing is, one key aspect of entropy is surprise, right? Yeah, you don't necessarily know what the results are going to be. And anybody who's done any coding, this idea of getting something that has got a life of its own is always kind of aspirational in a way. That's our holy grail, trying to get things that have got a bit of life to them, where you can't control things. So even setting up a process, a simple process where A might go with B or A might go with C. So the way in which we have some of the organization, we don't know what the results are going to be necessarily. And it might be a sound that I don't like, or it's maybe doesn't seem to work. But just creating processes in the code and the interactions leads to some of these things maybe that you're getting at here, where it's determined but not completely. Some of the combinations are indeterminate in terms of you couldn't actually predict exactly how an entropy with this waveform and this modulation the number of probabilities is still quite enormous, even with a simple set of probabilities rather, I should say. So ultimately, yes, I mean, I have quite a noisy aesthetic, so you could argue that sound is not a sound, but it's a complex kind of algorithm, really. It's like a piece, you could almost call it like a piece in its own right. It's when you switch it on and it's doing things, it's evolving. So I'm kind of drawn in terms of like aesthetics to those sorts of sounds. You know, that's maybe why it's not a synthesizer necessarily, maybe it's composition, where does instrument and composition begin and end? Those are the sorts of things, as a musician and somebody who works with technology, I'm fascinated about, that kind of overlap between composition, artwork, or is it just the sound? So in terms of aesthetic, that kind of noise aesthetic or sound or non-pitched material is something I'm drawn to. It doesn't have a keyboard, for example, and it's got a full spectrum. So we're dealing with sound and noise here, lots of different levels, and that's a driving kind of aesthetic motivation in many ways.
I guess also as a maybe more just kind of specific answer to that question about like, what are the kind of listening forms? I think like there was a time during the project where, because John and I don't live in the same place, and so there's only been a few times where we're actually able to be in the same place and listen. Actually, the synth only got finished because we went to Graz together and just were there for 3 days and really just spent the whole time writing code. But one of the things, and I guess John kind of referenced this earlier, that happened maybe in the months prior would be like, I would get excited about, I'm not as good at listening, I don't think. I'm not someone who sits and listens very well. And I think what would happen would be I would get very excited about a function that did something. I would send it to John, and John would immediately listen to it and go, it's got slower. And I think there was this long period in the collaboration where like, I think what was cool and like, I think what I came to be able to do and realize was like, I think that there's a kind of listening that one does when one works with a microcontroller that's all about this materiality of like speed and how completely interconnected the speed, the functionality, the sound is. And, you know, there was this kind of funny tension of I would come up with all these functions that did really complex kinds of modulation, and I would be like, we can do this bit of math. And at the end of the day, you can, but it makes the chip run slower, and there's a trade-off, really, with that, as well as the trade-off with the amount of space that you have.
I suppose it encourages a sort of broader idea of reduced listening. So you listen to a sound over and over again, and you get inside the sound, really, at all the micro levels, a kind of micro listening, especially when you've only got those limited parameters. So a sort of Schaeffer-esque idea of reduced listening. You're in it, you're in that one sound, and you realize that one sound is many sounds. So I think it draws me in terms of how I listen to sounds on that sort of level.
Thank you for the interesting talk. I was wondering, because you mentioned entropy, and I wasn't sure if I completely understand what you mean by entropy. Because from my understanding, it's like second law of thermodynamics. When you stay still, things just go to chaos eventually. So like there won't be negative entropy in the system. So in this case, in the microcontroller, what does that entropy mean? Does that mean that do you want to intentionally increase the entropy of the system or the sound it produces, or did I misinterpret what you try to do?
So,
Hold on. Mike.
thanks for that question. I guess that we are talking more about informational entropy, so Shannon entropy rather than Boltzmann entropy. It's a kind of classic engineering problem that they chose the same word for that, and they're related enough, but not quite related enough. In a sense, we're also faking entropy. We're actually keeping the informational content of our waveform exactly the same, but what we're doing is mimicking an entropic process by which a waveform which contains a lot of structured information, right? A sine wave is a kind of perfect waveform, if you like. That informational content, if you get sine waves in the wild, they'll degrade in all kinds of interesting ways. And, you know, the information in a sine wave might get passed down a cable. It might get noise in it. That's one of the simplest forms of entropy, right? If you're a communications engineer, you care so much about not having noise introduced in your sine wave signals that are carrying your frequency modulated internet information, right? But we just got quite entertained by vandalizing our like perfect wave in lots of different ways. And so we would think of ways to remove or otherwise change the wave tables information. And this is, in some senses, we're lying. We're producing this process entirely artificially. We just have a function that's called add noise, and we like have something that flips a bunch of bits in the wave. But I guess what we did enjoy experience. What also felt cool, and this maybe relates to the listening question, and maybe also the idiomatic question, is, at least for me, I'm used to working in environments where you have loads of memory, and I've not grown up with these limitations on audio in the same way, and actually hearing things that are bit crushed or hearing things that have been modified in these ways, like the bit crushed signals sound like really old, like 5, 6-bit. Do you have that? Like, chip tune stuff. You encounter different forms of like information loss that actually at different points have been totally limiting factors in communications and like audio design.
But like you said, entropy is quite a challenging word. There's a lot of different ways of approaching something entropic. I tended to make it more discernible in my head was, just look at the etymology of the word. Ent, which is inner, and I think trope is transformation. So basically, okay, the bottom line is I'm just thinking about inner transformations of some kind. But of course, it's associated with decay too. This is a big thing about entropy. Everything in the natural world has a kind of life. That's the death drive, which is also fascinating. But in terms of reduction, a reductionist approach in my head, we're looking at different inner transformations going on within the sound. Again, and that could be endless in the number of possibilities.
Yeah. I think my question, I mean, there's all sorts of questions, but I'll just try to focus this one around the critical making practice and how you try to disseminate it to other people through workshops. So you mentioned that, for instance, you can use sound synthesis to interrogate things about our reality, either how we listen or how technology is fabricated, distributed. So I was just wondering, like, when you're running a workshop, how do you approach that, like setting the tone for a critical making, or how you transfer it to the participants of the workshop, if that makes sense?
It's a good question. Next week I'm in Zagreb. I'm thinking, what am I going to do? And I've got to a stage where I've got so many components now. I've got a box of chips somebody gave me. In fact, I don't know what they all do, but there's just a whole box of random chips. Some of them are op amps, some of them are just old memory chips. So I might just turn up with the box of chips and say, we've got to reuse this stuff. Maybe that's a sort of reusing kind of metaphor, recycling kind of approach. So often, like with some of the papers I've been involved in, it starts with a theme. You might have a provocative theme that gets people thinking about, okay, so what are we going to make? I'm not just making a cool sound. Like I said, not anybody, but most people could make a square wave, like this. Maybe we start off with something a little bit more conceptual. Actually, Amit Patel here, we did a workshop in Denmark, which it had no sound output at all. Obviously, it wasn't one of the best attended workshops that we'd ever done. But the idea was that you would come to the workshop and make nothing. It was an experience. Yeah. it was a way of kind of breaking that idea that you take something away, perhaps, in terms of like a product. So often I would come with a theme or an idea that people would, I mean, you get that idea quite quickly when you turn up and you're actually making nothing. You suddenly realize, okay, what are we working on? What is this workshop? So that sort of thing can set the tone in terms of how you approach this kind of critical making. You have to come with hopefully a clear idea or a set of possibilities for people to explore beyond the sound itself.
So we usually drive with a set of questions?
Often, yes. And they can be durational. So it could be a couple of hours or it could be a week or, yeah, normally this kind of sort of hackathon style sometimes. Yeah, it's a bit like Bake Off. You've got to bake a cake and then you've only got 2 hours to do it. The kind of time limitations are also good because that imposes further restrictions on what you're doing. Of course, in the ideal world, we could design forever and improve things and get better and better at the stuff. But having a limited time, often intensive period, often physically where people come together, those are the kind of parameters that kind of move things forward in terms of tackling problems and doing these sorts of workshops. Hopefully helps.